Okay, so in the previous video, I was trying to explain the relationship between compiler design and um or the application of automata theory in compiler design, and I've been able to make you see why as how we need lexical analysis for next automata for lexical analysis using regular expressions. Of course, by regular expressions, you know that it's only finite automata. Well, not that it's only, but it's going to be an overkill if you use more powerful machines to try to solve problems of regular expressions. It's going to be an overkill. It's not going to be efficient, of course. And I was trying to say that online finite automaton cannot solve context-free grammar problems because they are inadequate. They don't have what it takes. And like I said, you get to know more on that in the next class. Okay, so let's look at derivation. So a derivation is a sequence of production rules in order to get the input string, because of course this is what you did in grammar. You have production rules, you have the terminals, you have the non-terminals, and you try to replace them. Now the main thing you're trying to can doing grammar now can be can be put into two. The first is, we can say that you are trying to on decide on the non-terminals to be replaced, then deciding on which rule to use to replace the non-terminal, and also finally to then determine which terminal to then use to replace the non-terminal. Deciding the non-terminal which is to be replaced, deciding the production rule by which the non-terminal will be replaced, and to decide which non-terminal to be replaced with the production rule. Now, in doing this, there are two ways by which you can do it. First is through the left derivation. Now, in the leftmost derivation, you're trying to replace the non-terminals from the left. But in the right derivation, you are replacing it from the right. Of course, these are things you did in um on grammar. I'm just revisiting it, and like you have in this example, the one on top, you have the you can see it's coming from the left, then you place it till you get to the right. Why the one from the right? You keep replacing from the right till you get to the left. So the one on top is called the leftmost derivation, while the lower one is the rightmost derivation. Now, string recognition. How does the compiler recognize strings? When I was compiling this lecture, I think this particular well, it's gonna work for most programming languages anyway. But I think this one was for Fortran. I think this one was for Fortran or Pascal. Now, but in any programming language, letters go from A to Z, small letter or capital letter. Those are letters. Basically, if you want to write your strings or things like that. What about digits? Of course, digits goes from 0 to 9. Digits, just digits, just digits. What about digits? Digits first have the digits, then digit star. I hope you understand the difference between the two, digits and register. Digits is, of course, you have to have it, even if it's just zero, it's just one. You must have one thing there before it can be a digit. Then, if you now have something afterwards, digit star. Don't forget that the star behind means that it is a star closure. Star closure in the sense that it is binding over all possible strings of all possible lengths that can be generated from digits, inclusive of the string of empty length, which is lambda. That means that if you just have one lambda, of course, one lambda is one, or zero lambda, that's what, then one is a digit, then digit star. Of course, you can have one, two. That means that, yes, digit star It can be anything in any combination in any manner. What about identifiers? In any identifier, you can have the listing. You must have a letter. Then you can also have a combination of numbers and letters. That's why you have letter. Then you have letters or numbers or underscore star in any manner, in any form. That's what that means. But what about fractions? Fraction, you must have the dots. You must have the digit or the exponential. But what about the exponential now? You can have e. You can denote it with e, and you must then raise it to a power using the positive or the negative. Positive is if it's having zeros behind the decimal figure or zeros before the decimal figures. Then next one is um operations. uh, op- so the next one is a number which can be a in form of digits, fractions, and exponents. Then you have operators, various types of operators depending on the programming language that you are using. Then finally parentheses, which can be the left curly brace or the right curly brace. Now let's bring this home. FSM for recognizing identifiers on a compiler. In any programming language that you may be writing, there's no how you will need identifiers. Identifiers could be to identify a particular variable or a particular function, or you want to assign something. How does the compiler recognizes identifiers? So we have this FSM. Actually, don't forget that I didn't design this myself, but just understand it. So of course, if I were to design this, I will have to still be. I will start considering security in the sense that I won't start trapping. But leave all those complexity out now. Just understand it. So we have the letter. After the letter, we have letter or digister. Like I explained, letter or digister that you're seeing over there is a clean is a star closure. That means that you can have letter. If you have more letters after the first letter, then you go to the final state. But even if you don't have more letters, it will just lambda, which is a string of empty letters. So just have the letter, then lambda, which is going to be the letter. A lambda is still A, B lambda is still B. So that means you could still get to your final state. Or if you want to start with an underscore, so you have the underscore, you have the letter or the digit star, which is you want to mix it up with the letters now or the digits in any manner. Is already an identifier at that point. Then you go to your final state. So this for the programming language, I think it's Pascal that it was designed for, will identify a yes, will pass an identifier. This FSM will pass an identifier in the programming language it was designed for. Now let's look at what about integers and floating point numbers on this compiler. Now you can see that we started from, okay, again, don't leave the complexity of security and all out for now. Just to understand the basic rule. Of course, if you were to design it, I won't expect that you just have it like this. I will expect you to design the security with it so that if it's not a floating point number or if it's not an integer, it traps it. But for those people that just want to understand it, they just understand this basically. So now you have the digits. If you have more digits, you can loop it over on top. At that point, if it's just digits you needed, of course you know digits or digits. Now, from just like what we did before in the previous slide, the previous slide that considers the digits, okay, that considered um identifiers. Now, this digit that you have on top, it's same thing as digister, because what does it mean that why is it also the same thing as digister? Because at this point when you have digits, you're already in a final state. So if it's just so digits is one. So don't forget, like I said, one and one ladder are the same. So one, you're already in a final state. So you still want to pass line and it's still the same. But if you want to pass one, two, you pass one, then the digit on top will loop what happens after. You have the dots, which is very important. So once at that point that you have digits or more digits, you are passing a floating point number. And if you want to use the exponential values to represent your floating point number, so at the point of number 2, you can use the capital E or the small e. If you use capital E or the small e, you need to raise up to a power, because that is the rule for using e for floating point number. It has to be e plus or minus 0 point something like that. So if it is e raised to power 2, of course that's positive 2 now. It's going to pass either that or that. Then the digits that's going to have, you must have a digit there obviously compulsorily. Then you can then get to your final state like that. You can, so all of these are used for um compilation of programs on a computer language. Sorry, using in a computer language, in a computer language. So the next one, let's look at how we can recognize relative operations. Of course, you know relative operations like greater than or equal to, less than or equal to, and the likes. So let's start from top. So if you want to, I think like this is designed for Pascal. You see why I said designed for Pascal now. Now, less than or equal to, you can say from 0 to less than, you are on state 1, equal to. So the syntax analyzer is going to return relative operation less than or equal to. If you have less than, then at from 1 you go to 3, which is greater than, that is not equal to. Like I said, this is for Pascal. And even like program language like PHP or Java, and it's going to be exclamation mark equal to. So the other is just to cater for what else that may come. But basically at that point, what you want to just have is just the less than on its own. Then any other thing you put is going to be the value that you want to compare to, and that just less than that. You have why you have LT over there. Same thing goes for the equal to. If you are starting from point zero, and you go to 5, that is the equality sign. That is relative operation. That's equality. So same thing for the greater than. For the greater than from point 0 to point 6, then if you go to that, that will be greater than or equal to. That's why we have this operation GE, that's greater than or equal to. But if you have just the greater than up to this point 6, then you go to point 8, that you want to put maybe the value you need to want to compare with. Of course, having start there also, which is string of all positive string of all possible length, including inclusive of the string of empty length, which is lambda. Then you have the greater than um that's going to pass greater than for you. So these are various ways which you can pass up every almost everything that you may need on a computer programming when you're writing programs, or when you're writing program code for a particular programming language. So this is how your programs are compiled, from lexical analysis to syntax analysis and semantic analysis. So you have an assignment again. Design a finite state machine for a compiler to pass complex numbers while reading the least significant figure first. Don't forget, you're not reading the MSB first here. You're reading the LSB first. That means that you want to read it in reverse order. So I would like to see the alphabet. Test out your design, then obtain the format description. Please, I'm not going to extend the submission time for this assignment. So I expect that you guys will submit it today before 10 p.m. So it's just a single assignment today. So this is the last slide, I guess. Next week we're going to finite state transducers, of course, still under regular expressions. So afterwards we go into something different from finite state automated and finite state transducers. We try to go into applications of the context free grammar. Thank you so much.